Welcome back to the Deep Dive. Today you're joining us as we navigate a crucial frontier in autonomous vehicle technology. How these vehicles can simultaneously sense their surroundings with high precision and communicate vital information at lightning speed.
Yeah, it's like solving a really complex puzzle.
Exactly. Where seeing and talking need to happen perfectly, all while, hurtling down the road.
What's truly fascinating, and the core of the challenge we're exploring, is the incredibly dynamic environments these vehicles operate within. It's not a static lab. It's a constant flux of movement, obstructions, and, well, unpredictable wireless conditions.
Mhm.
This puts immense strain on the underlying technology that allows them to perceive and interact.
Exactly. And today, our mission is to dissect a really ingenious approach aimed at tackling this very problem. We're diving deep into a research paper that proposes a novel way for autonomous vehicles to intelligently manage their communication and sensing using something called reinforcement learning and adaptive orthogonal frequency division multiplexing, or OFDM. We're zeroing in on the technical mechanics of how this system is designed to handle the ever-changing realities of the road.
And just to set the stage, the research paper you share explores this joint adaptive OFDM and reinforcement learning design specifically for autonomous vehicles. A key element they investigate is leveraging the age of updates, a concept that's pretty central to their innovation,
Yeah.
and something we definitely need to unpack so you can see its significance.
Okay, let's unpack this. Let's start with the fundamental problem this research is trying to solve.
Mm.
The paper points out that current systems often rely on preset static configurations for the mmWave technology these vehicles use.
Mm-hmm.
They decide things like how many pieces of data go into each transmission frame ahead of time.
Mm-hmm.
But as we all know from driving, the real world throws curveballs constantly.
Precisely. Millimeter wave communication, while holding incredible promise for vast amounts of bandwidth, which is essential for both detailed sensing and rapid data exchange, is also notoriously finicky when it comes to its environment. Anything that gets in the way of a direct signal path or creates interference can have a substantial negative impact. It's a bit like trying to get a clear picture on an old TV antenna. Even a small shift can cause big problems.
And it's not just about seeing in a passive sense, it's about actively ensuring safety. Autonomous vehicles need to seamlessly integrate sensing like radar that bounces signals off objects with communication, often referred to as V2X or vehicle to everything.
Yeah, that integration is key.
This allows them to not only detect obstacles in other vehicles, but also to estimate their speed and receive real-time information from nearby vehicles or roadside infrastructure.
And if we connect this to the bigger picture, think about the limitations of older vehicular communication technologies like DSRC and CIs. While they serve certain purposes, their data carrying capacity isn't really designed for the future needs of fully autonomous driving. As these systems become more advanced, with applications requiring the sharing of massive data sets, very quickly imagine vehicles coordinating complex maneuvers or sharing detailed sensor readings. These older technologies might simply hit a data bottleneck.
This is where millimeter wave technology steps in, offering the potential for that much-needed high bandwidth. It's the key that could unlock both ultra-high-resolution sensing, giving a very detailed picture of the surroundings, and the rapid data transmission required for those advanced applications.
But, as we've underscored, it's vulnerable. Environmental changes and the necessity for extremely precise antenna alignment between vehicles pose significant technical challenges.
It's like trying to thread a very fine needle while everything is moving.
Exactly. And the critical point this research paper makes is that many of the existing approaches haven't fully embraced this dynamic nature. They tend to use these static, predefined waveform parameters and haven't adequately accounted for the unpredictable and ever-changing environments that autonomous vehicles must navigate.
So this leads us to the core of their proposal, a joint adaptive OFDM and reinforcement learning approach. Now, for those of you who might not be experts in telecommunications, OFDM is a clever way of packaging digital information onto multiple radio frequencies simultaneously, which makes the communication more resilient against disturbances in the signal. Think of it like sending a message by having many people whisper parts of it at the same time on slightly different pitches. If some whispers get lost, the overall message still gets through.
And what's particularly innovative here is that they're making this OFDM adaptive. The fundamental idea is that an autonomous vehicle would continuously monitor the state of its communication queue, how much data is waiting to be transmitted, along with detailed information about the quality of the wireless connection, known as channel state information.
Okay.
This real-time data is then fed into a reinforcement learning system, which acts as the intelligent brain making decisions about how to best manage both communication and sensing resources.
This intelligent management aims to achieve two primary goals. First, to maintain a stable and dependable communication link with other autonomous vehicles, crucial for exchanging time-sensitive safety information.
Right.
And second, to obtain highly accurate estimates of the velocities of surrounding objects. That precise velocity information is absolutely critical for functions like, well, avoiding collisions.
To assess how effectively the communication link is performing, they look at several key indicators: the length of the data queue itself, the effective data rate, the actual amount of useful data that's successfully being transmitted,
Yeah.
and the rate at which data packets have to be discarded because the system is overloaded or the signal is too poor.
And on the sensing front, the main measure they're concentrating on is velocity resolution, essentially.
Yeah.
How precisely the vehicle can determine the speed of other moving objects.
Yeah, the finer the resolution, the better the understanding of the environment.
Now, the adaptive aspect we mentioned earlier really shines through with the OFDM. The system has the capability to dynamically adjust its modulation scheme.
Right. Think of a modulation scheme as the method used to encode the digital bits of information onto the radio waves. More sophisticated schemes can pack more data into the same amount of radio wave, leading to faster transmission, but they are also more susceptible to interference. It's like trying to write very small, you can fit more on a page, but it's harder to read if the page is blurry.
And a truly central component of their innovative system is a reward mechanism that leverages something called the age of updates, or AOU. This is used not only to manage the flow of data in the communication buffer, but crucially to also enhance the accuracy of the sensing data. We definitely need to delve into what AOU actually represents and why it's so important.
Absolutely. And to validate the effectiveness of their proposed system, they employed two well-established reinforcement learning algorithms: Advantage Actor Critic, often abbreviated as A2C, and Proximal Policy Optimization, known as PPO. These are advanced machine learning techniques that allow an agent in this context, the autonomous vehicle's control system, to learn the most effective strategies for managing its resources through a process of trial and error within a simulated environment.
Okay, let's really get down to the technical nitty-gritty, starting with this age of updates. You've mentioned it's a cornerstone of their reward function. So in simple terms, what exactly is AOU?
In essence, AOU quantifies how much time a data packet spends waiting in the transmission buffer from the moment it arrives until it's successfully transmitted.
Okay.
Now, it's important to distinguish this from a related idea called age of information, or AOI.
Ah, right.
AOI.
AOI measures the time that has passed since the generation of the most recently received successful update. So AOU focuses on the delay within the sending process itself.
So AOU is specifically tracking the lag within the vehicle's own communication system before it sends out information.
Exactly. And the researchers here cleverly integrate AOU into their reward function as a way to prioritize getting fresher information out in those vital vehicle-to-vehicle communications.
Makes sense.
The underlying principle is that by penalizing older, stale updates, the system is incentivized to strike a better balance between keeping communication delays low and ensuring that the velocity estimations derived from the sensing data are based on the most current information.
Right.
You want the most up-to-date picture of what's happening around the vehicle to inform its actions.
That makes perfect sense. Now, you also mentioned that they framed this problem as a multi-objective reinforcement learning challenge. What does that involve? It signifies that they're not trying to optimize for just one single performance metric, but rather for several different and often competing objectives simultaneously.
Okay.
In this scenario, the system isn't aiming for a single best outcome, but rather navigating trade-offs across things like maintaining a short queue of data to be sent, achieving high radar accuracy in its velocity measurements, and minimizing the number of data packets that get dropped due to network congestion or poor signal.
So multiple goals.
These are all important, but might necessitate different actions from the system, you know?
So if you have multiple goals, how do you actually get algorithms like PPO and A2C, which typically work with a single measure of success, to handle that?
That's a crucial question. They address this using a technique known as linear scalarization. Essentially, they assign a weight or level of importance to each of their objectives, for instance. A certain weight for keeping the cue short, another for achieving high radar accuracy, and yet another for minimizing dropped packets. They then multiply each of these performance measures by its corresponding weight and sum them up to get a single overall reward value.
Oh.
This single value is what the RL algorithms then use to guide the learning process and optimize the system's behavior. The choice of these weights is critical because it directly influences the compromises the system will make between these potentially conflicting goals.
Now let's delve into their adaptive action state framework. It sounds like this is where the real-time decision-making magic happens.
Precisely. The action set, the range of choices that the reinforcement learning agent can make at any given moment, isn't fixed. Instead, it's a combination of selecting a specific modulation scheme, which determines how densely they pack the digital information into the transmitted signal,
Right.
and choosing the size of the OFDM frame, which is essentially how many of these modulated symbols are grouped together for transmission at once.
And what about the state representation? What information does the system have access to when it's deciding on these actions?
A key piece of information in the state is the signal-to-interference plus noise ratio, or SINR.
Similar. Okay.
Think of SIN as a measure of how strong the desired signal is compared to any unwanted signals or background noise. A higher SIN generally indicates a better quality connection.
Right.
By including SIN in its awareness of the current situation, the system can intelligently adjust its data transmission strategy based on the prevailing wireless conditions. For example, if the SINR is high, indicating a strong, clear connection, it might opt for a more complex modulation scheme to achieve a higher data transfer rate.
More bits per symbol.
Exactly. Conversely, if the SINR is low, suggesting a noisy or weak connection, it might switch to a more robust but lower data rate modulation to minimize errors and prevent data loss.
Got it.
The range of modulation schemes they consider goes from basic binary phase shift keying, BPSK, which transmits 1 bit per symbol, all the way up to 64 quadrature amplitude modulation, 64 QAM, which can pack 6 bits into each symbol.
6 bits. Wow.
And the number of frames in the action set can also be varied dynamically, from just 1 up to a predefined maximum.
So it's constantly taking a snapshot of the communication environment and then selecting the most appropriate way to send and receive data at that precise moment.
Exactly. Now let's dig a bit deeper into how they model the communication channel itself. This is crucial for creating realistic simulations and understanding the challenges the system faces.
Right. You mentioned attenuation modeling using a log-distance path loss model at that specific 60 gigahertz millimeter wave frequency. What are the important factors they consider there?
At these very high frequencies, the strength of the radio signal decreases quite rapidly as the distance between the transmitter and receiver increases.
Yeah.
The log-distance path loss model is a common way to mathematically represent this general trend.
Standard stuff.
Yeah, but for vehicles on the road, you also have to factor in obstructions. The researchers incorporate what they call channel blocker coefficients to represent different levels of blockage in the direct line of sight between the communicating vehicles.
Okay, blockers.
They consider scenarios ranging from having no obstructions, line of sight or LARS, to having 1, 2, or even 3 other vehicles physically blocking the signal path. Each of these different blockage scenarios has an associated probability of occurring and different parameters for the path loss model itself, such as the rate at which the signal weakens with distance, the path loss exponent, and a constant value,
Right.
which together reflect the increased attenuation caused by the blockage. They also take into account atmospheric attenuation, which is a relevant factor at 60 gigahertz frequencies.
And then there's the very real challenge of antenna alignment, which you touched on earlier.
Yeah.
Millimeter wave beams are incredibly narrow, aren't they?
That's correct. This narrowness is essential for focusing the transmitted power and achieving high signal gain. But it also means that the transmitting and receiving antennas need to be pointed at each other with very high precision.
Which is hard when moving.
Exactly. In a dynamic setting where vehicles are constantly moving and changing their orientation relative to one another, maintaining this precise alignment is a significant engineering challenge. This necessity leads to the use of time-slotted communication.
Time slots, okay.
A portion of each communication time slot must be allocated to beam alignment, the scheduling time, to ensure the antennas are correctly oriented before the actual data transmission the effective data transmission time can take place.
So there's overhead.
There's overhead, yes. The likelihood of misalignment occurring and the resources required for the alignment process depend on factors like the relative speed of the vehicles, the narrowness of the antenna beams, and the duration of the pilot signals used for the alignment.
Got it.
The SINR, which we discussed earlier, is also directly influenced by the gain of the antennas at both ends of the link, the power of the transmitted signal, any interference coming from other nearby transmitters, and the level of background electronic noise.
What about the data itself?
Mhm.
How do they model the flow of information and potential delays within the communication system?
They model the arrival of new data packets at the receiver's queue as following a Poisson distribution, which is a standard statistical way to represent events occurring randomly over time.
Okay, Poisson.
For each discrete time slot in their simulation, they calculate the length of the queue based on how many packets were waiting at the start of the slot, how many new packets arrived during that slot, and how many packets were successfully transmitted based on the available channel capacity and the chosen transmission parameter.
And if a queue gets too full?
If the number of packets in the queue ever exceeds the maximum size of the buffer, any newly arriving packets are considered to be dropped. This allows them to quantify the rate of packet loss, which is a critical measure of the communication system's reliability.
Okay, so that gives us a good picture of the communication side. What about the sensing channel modeling? How does the radar functionality fit into this framework?
Their model assumes that the sensing process is triggered in conjunction with the communication attempts. In the time slots where there isn't active data transmission occurring, they propose sending what they term jamming data.
Jamming data.
Yeah, it's a bit of a term, but essentially filling the silence. Furthermore, they consider a single communication time slot to be composed of multiple individual OFDM frames. For their radar functionality, they utilize the IEE 802.1A SCPHY frame structure, which includes a preamble containing Golay sequences.
Lay sequences, right.
These sequences have desirable mathematical properties, specifically in terms of their autocorrelation, which makes them well-suited for radar tasks like estimating the distance to objects.
Right.
However, they are also sensitive to Doppler shifts in the frequency of the received signal, which is caused by the relative motion between the sensor and the target, and this affects the accuracy of velocity measurements.
The Doppler effect.
To improve the precision of these velocity estimations, they incorporate a technique called multi-frame processing, where data from multiple consecutive frames is analyzed together.
How does the movement of the vehicles and the resulting Doppler shifts impact the ability to sense accurately?
The Doppler shift is directly proportional to the radial velocity of the target, how fast it's moving directly towards or away from the sensor. A larger Doppler shift corresponds to a higher relative speed.
Makes sense.
However, a large spacing between the subcarrier frequencies in the OFDM signal can actually degrade the orthogonality between these subcarriers due to these Doppler shifts. This degradation can interfere with the signal processing.
Okay.
To maintain the integrity of the signal processing, there is an inherent limitation on the maximum relative velocity that can be accurately sensed, and this limit depends on the specific parameters of the OFDM waveform being used.
And how do they define the precision of their sensing? You mentioned they're particularly focused on velocity.
Radar resolution in general refers to the minimum separation in either distance or velocity that's required to distinguish between two distinct targets. While achieving good distance resolution is often more straightforward in many radar applications, improving the resolution of velocity measurements is more challenging, primarily due to that sensitivity to the Doppler effect we just discussed. Additionally, increasing the number of frames used for velocity estimation while improving accuracy can also consume more communication resources and potentially lead to congestion on the shared communication link.
Right, that trade-off again.
Exactly.
Okay.
Therefore, the researchers in this paper place a priority on optimizing the velocity resolution. They mathematically define the precision of the velocity measurement in terms of the root mean square error, which is a statistical measure of the average magnitude of the errors. Yes, RMSE. This error is shown to be a function of the signal to interference plus noise ratio, SINR, of the received radar signal and the number of OFDM frames that are used for the velocity estimation. Generally, a higher SINR and the use of more frames for processing lead to a more precise, lower error velocity measurement.
So the system is in a constant balancing act between using more data for better sensing accuracy and using fewer resources to keep the communication channel open and the data flowing efficiently.
Precisely. Now let's delve into the specifics of the reinforcement learning implementation itself. How is the RL agent actually structured and trained to learn these optimal decision-making strategies?
You mentioned the state space and the action space earlier. Can you elaborate on what constitutes the state the agent observes and the actions it can take within this reinforcement learning framework?
Certainly. The state that the reinforcement learning agent perceives at any given point in time is characterized by two key pieces of information. The current length of the data queue, essentially, how many packets are waiting to be transmitted,
Okay, queue length.
and the instantaneous signal-to-interference plus noise ratio, SINR, which provides a measure of the current quality of the wireless communication link.
And CNR.
Got it. The action that the agent can then choose to take is a combination of two parameters. First, the selection of a specific modulation size, which dictates how many bits of digital data will be encoded into each transmitted symbol.
Modulation choice.
And second, the number of OFDM frames that will be transmitted in the current time slot.
Number of frames. Okay.
And how does the agent actually learn which actions to take in different situations?
The agent's objective is to learn an optimal policy, which is essentially a learned mapping from the observed states to the actions it should take. The goal of the entire reinforcement learning training process is to discover a policy that maximizes the expected return, which is the total cumulative reward that the agent receives over time by interacting with the simulated environment.
Maximize reward over time.
Exactly. In this research, they utilize policy gradient methods, specifically proximal policy optimization, PPO, and advantage actor critic, A2C, to achieve this learning.
PPO and A2C.
These are categorized as actor-critic methods, meaning they have two main interacting components. An actor that is responsible for deciding which action to take based on the current learned policy, and a critic that evaluates the value of being in a particular state, providing feedback to the actor about how good its chosen actions are. The advantage function plays a crucial role here. It quantifies how much better a specific action is compared to the average action that could be taken in that particular state.
You also mentioned the PPO clip objective function. What's the purpose of that clip mechanism in PPO?
The PPO clip objective function is a clever technique designed to ensure the stability of the reinforcement learning agent's training. It works by limiting how drastically the learned policy can change during each update step.
Okay, so stability.
It does this by comparing the ratio of the probabilities of taking a particular action under the newly proposed policy versus the old policy with a predefined range or clip. If this ratio falls outside of this allowed range, it is artificially constrained or clipped to stay within the bounds.
It prevents big jumps.
Exactly. This clipping mechanism prevents the policy from undergoing excessively large and potentially destabilizing changes during the learning process, leading to more reliable convergence.
Okay, let's circle back to that all-important reward function. You mentioned it cleverly incorporates the age of updates. Can you explain in more detail how it's structured?
The proposed reward function is composed of three primary components, each assigned a specific weight that reflects its relative importance in the overall objective. The age of updates of the packets currently in the transmission queue, the accuracy of the radar velocity measurements,
Velocity accuracy.
and the rate at which beta packets are being dropped.
Dropped packets, okay.
The overall reward that the agent receives for taking a particular action in a given state is calculated as a weighted sum of these three terms. Notably, the AOU and the dropped packet rate contribute negatively to the reward, as the goal is to minimize these, while the velocity accuracy contributes positively, as the goal is to maximize it or equivalently minimize the error.
So, reward high accuracy, penalize delays and drops.
Precisely. This reward function is specifically designed to be an improvement over a previous reward function that only considered the queue length, velocity accuracy, and dropped packets, without explicitly accounting for the freshness of the information using AOU.
Right, adding that AOU term is the key difference.
By incorporating AOU into the reward signal, the agent is incentivized to prioritize the transmission of older packets, thus ensuring that the information circulating in the vehicle-to-vehicle communication links remains more current, which ultimately benefits both the latency of communication and the accuracy of the velocity estimations derived from the sensing data.
So the agent learns to make these dynamic decisions, choosing the best modulation and the optimal number of frames to transmit in a way that not only leads to more accurate sensing and more reliable communication, but also ensures the timely delivery of the most relevant information.
Exactly. Now, let's move on to the findings from their extensive simulations. What did they actually observe when they put this proposed system to the test in a realistic setting?
They conducted simulations using a comprehensive set of parameters, many of which are detailed in their research paper. These include specifications like the number of subcarriers used in the OFDM modulation, the maximum allowable number of frames in a transmission, the range of available modulation orders,
Uh-huh.
the carrier frequency and bandwidth of the millimeter wave signal, the relative range and velocity of the simulated vehicles, the assumed level of background noise, the gain of the transmitting and receiving antennas, the power of the transmitted signal, the levels of potential interference from other sources, and those crucial path loss parameters we discussed earlier that account for different types of signal blockage.
A lot of parameters.
Yeah, pretty detailed. They also set various parameters related to the simulation duration, the learning rate of the reinforcement learning algorithms, and the specific weights assigned to each component in that reward function we just talked about.
And critically, they evaluated the performance of their system under a range of different channel conditions, specifically categorizing them as poor, normal, and strong.
Right.
These conditions were defined by the statistical probability of encountering different types of signal blockages and the resulting expected packet error rates.
So what were the key results? What were the most significant takeaways from these simulations?
One of the most compelling findings was that the proposed system, the one that incorporates the aged updates into its reward function, demonstrated a clear improvement in the normalized average reward achieved compared to a baseline system that didn't use AOU.
Better reward with AOU.
This consistent improvement was observed for both of the reinforcement learning algorithms they tested, A2C and PPO, suggesting that incorporating AOU leads to both better overall performance and a faster rate at which the learning process converges to a good solution.
That's a pretty strong indication that this idea of tracking the age of information is really paying off. What about the specific performance metrics they were tracking, like the length of the data queue, the accuracy of the velocity measurements, and the number of dropped packets?
They meticulously analyzed these metrics under the various simulated channel conditions and also by varying the rate at which new data packets were arriving in the transmission queue.
Okay.
In challenging poor channel conditions, they noted that the PPO algorithm sometimes exhibited a plateau phase where key performance indicators like queue length, the rate of dropped packets, and the effective data rate would temporarily stagnate before eventually showing further improvement.
PPO plateaued sometimes.
Yeah, a bit. Interestingly, the A2C algorithm demonstrated better stability and overall performance in these more demanding and rapidly changing environments.
Ah, so A2C was maybe better in the tough spots.
Seems like it. Importantly, their proposed scheme, utilizing both AOU in the reward function and the adaptive modulation of the OFDM signal, achieved significant gains in both the precision of velocity sensing and the effective data transmission rate across all tested channel conditions, poor, normal, and strong, when compared to the theoretical maximum performance limits defined by the IEE 802.11 ad standard.
So real gains compared to the standards limits.
Big time. To give you some concrete figures, they reported achieved velocity resolutions as fine as approximately 0.71 meters per second in poor conditions, improving dramatically to around 0.064 meters per second in strong conditions.
Wow, that's a huge improvement in velocity accuracy.
Yeah. Simultaneously, the effective data rates range from a solid 1.88 gigabits per second in poor channels up to an impressive 6.58 gigabits per second when the channel conditions were strong.
Those are really significant improvements, especially getting that close to the theoretical limits of the standard. It highlights the efficiency of their approach.
Indeed. They also emphasized the robustness of their system, even when the rate of new data packets arriving was high, particularly when the underlying communication channel conditions were strong.
So it handles heavy traffic well, too.
Right. This suggests that the system is capable of effectively managing its resources and maintaining good performance even under heavy data loads. The overall conclusion drawn from their simulation results was that the age of updates is indeed a valuable metric to consider when optimizing the communication waveform in dynamic environments, as it enables a much more effective balance between the demands of high-throughput communication and the critical requirements of accurate environmental sensing.
So to bring our depth dive to a close today,
the central takeaway is that this research presents a truly promising technical advancement, a combined adaptive, OFDM and reinforcement learning system that intelligently utilizes the age of updates to significantly enhance the capabilities of integrated sensing and communication systems for autonomous vehicles operating in those complex and ever-evolving real-world environments.
And the key technical innovations seem to lie in the intelligent way they dynamically manage communication resources based on real-time information about the data queue, the quality of the communication channel, and the freshness of the information,
Right.
coupled with the ability to adapt the modulation scheme on the fly. These advancements directly translate into improved accuracy in sensing the speed of surrounding objects and more reliable data exchange.
This leads to a final thought for you, our listener. Consider how these technical principles of intelligently managing information freshness and dynamically allocating resources could potentially be applied to other complex multi-agent systems beyond just autonomous vehicles.
Interesting question.
In what other domains where timely data and efficient communication are paramount for optimal operation and decision-making? Could prioritizing the age of information and adapting communication strategies in real time lead to significant improvements in system performance and overall reliability?
Yeah, think about scenarios where ensuring the information used for control and decision-making is as up-to-date as possible could be a game changer, like distributed robotics or maybe even smart grids.
Definitely a fascinating area to consider further. If you're interested in delving even deeper into the technical details of artificial intelligence and machine learning research, be sure to visit our webpage. The link is conveniently located in the episode description. Thanks for joining us for this deep dive,
Thanks, everyone.
and we look forward to exploring another fascinating topic with you next time.